Very broadly, I study planet formation. More specifically, I observe the process of planet formation around other stars. So I'm just going to talk to you briefly today. I'm just going to talk about how stars form, how planets form, and the sort of things we look for when we try and observe these processes. So to really understand planets, you need to look back and see how stars form, where they come from. And like most things in the universe, they begin life as clouds. These great big clouds of dust and gas, or mostly, gas, sorry. And this is the Taurus molecular cloud in the constellation of Taurus, strangely. And this is just this is one huge, great big cloud of gas. And this is what it looks like in visible light. So this is what you see with your naked eye. So if you look for a telescope, you'd see a great big brown smudge across the sky, which is, it's a brown smudge. It's not very useful. This is the same cloud, but this is looking in millimeter wavelengths, so much longer than our eye can detect. And you can see there's a lot more going on now, because we're looking at the slightly warmer regions of gas within there, and you can see that there are hot spots, there are cool spots, there's these weird filament structures, there's all sorts going on, there's things moving, there's things happening inside these clouds. And inside these clouds, you have smaller regions, smaller clumps of higher density regions. So there's a bit more stuff in these regions than there is outside them, and these regions are contracting. They're falling in on themselves. There's enough mass there that the gravity takes over and they start to fall in. And as they fall in, their pressure builds and they get hotter and hotter. And the core of these regions is more dense and it falls in even quicker and it gets hotter and hotter and hotter until eventually you have a star, or a protostar. It's a very young, very big, very dim star, still surrounded by lots of dust and gas, but it is the very first star being born, right inside your giant clouds. And these don't tend to form just on their own. You get huge clusters of them forming at once. And we can model these. So I've got some nice videos. These are stolen from Professor Matthew Bate, who works at the University of Exeter as well. And he's basically built this giant simulation and filled it with a great big molecular cloud. This is full of gas, and when it starts playing, you're going to see it. So you can see it starting to twist and turn, it's starting to collapse a little bit. You've got these denser regions which start to contract together. And as it goes on, you will see, very slowly, some little spots start to form. And over time, they start to fly out. And they're coming out all over the place. And you can see the years go by. This simulation here lasts about 100,000 years, so it's not a quick process, this. These clouds collapse slowly and form in, and you can see that by the end, we've got quite a lot of stars. You can maybe count a few dozen, and if you let this simulation run to completion, you end up with just under 200 stars forming in this one region. And so these are not isolated events. These are happening in star-forming regions across our galaxy. So we've got a star now. Good, we need a star for a planet. But where do the planets come from? Well, it's only the core of these clumps that form the stars. There's still this envelope of material around the stars. And these stars are now spinning quite quickly. So we saw in the video that the whole molecular cloud was rotating quite slowly, a bit of movement there and there, it's twisting, it's turning. But as things contract, they speed up. It's the conservation of angular momentum. So as things contract, they have to speed up to conserve the angular momentum that's going on. So we can see this quite nicely, if this is going to work. Yeah, so if I skip to about here in the video, so here we've got, this is Victor, one of our postdocs, and he's sat on a spinning chair. He's got his arms out, he's got his legs out, he's a nice big molecular cloud spinning round in space. And he's spinning fairly slowly, he's just been set going and he's going round. And in a minute, he's going to contract, he's going to make a star. He's going to pull his legs in, pull his arms in, and he's going to speed up. And this is the conservation of angular momentum. No one's going to give him an extra push, he's just going to speed up. And we get the same view from the top too, just to... And you can try this at home if you fancy. Just don't fall off and blame me. So yeah, these stars are spinning quite quickly now, and the dust around them is moving quite quickly too. And this creates centrifugal forces. So, and these forces, they'll be quite strong, they'll be really strong at the equator. So at the equator of your star, you've got the strongest forces. And this pulls the dust downwards and inwards, and it flattens the material. And we end up with a really flat disk around our star, roughly around the equator. And at the poles, where you have the weakest centrifugal forces, the material is ejected up in long jets from both the north and the south pole. And you end up with something that looks a little bit like this. So this is, of course, an artist's impression. We can't take images quite this nice. But you can see the nice flat disk around the centre, or on the equator of the star, and then erupting from the poles, you've got these enormous jets of material. And this on the right, this is a real image that we've taken, or that I didn't take, but was taken with the ALMA array. So all the real images I'm going to show were taken with the ALMA array. Much like the interferometer that Ian just talked about, it's an interferometer like that Ian just talked about with planning to make with Goonhilly and Jodrell Bank. But this is an array in the Atacama in South America, and it consists of 48 telescopes, all observing in sub-millimeter, all observing simultaneously up to 12 kilometers apart. And you can create these wonderful images of these disks. And you're looking imagine you're looking from the top of this image, you'd see something a bit like this. You've got the orbits of Pluto and Neptune overlap there, and you can see the extent of this disk. It's a huge disk. And so eventually this will form a huge planetary system. So yeah, we've got a star now, and we've got a disk of material from which we can make some planets. And now we go from some quite nice animations to my crude animations of what happens in these disks. So we've got the issue is with these disks, they're 99% gas and only 1% dust. And it's this dust which we need to make planets. So we're already a bit of a disadvantage. And this dust is sort of just milling around, bumping around, jostling around all over the place, and occasionally two of them bump together. And 95% of the time when they bump together, they either just shatter or they bounce off each other, which is pretty useless. But then 5% of the time, they might stick together. So these particles all have some weak electric force. They have a bit of electromagnetic force that sticks them together. And over very, very long periods of time, more and more stick together. And you can build up from something that's less than a micron, so microscopic in size, to something up to a kilometre in size. And when you get to around a kilometre, you have something we call a planetesimal. It might be roughly spherical in shape-ish. It's a bigger object, and it's a baby planet, basically. We have lots of objects like this in our solar system. We call them asteroids. They're in the asteroid belt. And we just don't call them planetesimals because they're unlikely to form planets for a few reasons. There's just not enough material, and they're being perturbed by all the other planets. So yeah, we call them asteroids generally. But in other systems, they're planetesimals. And once you have something that's about a kilometre in size, gravity can start to take over again, and you can start, and as the object moves through the disk, it can attract all the nearby dust to it. And so it grows a bit more quickly now. And we can go from something a kilometre to something that's thousands and hundreds of kilometres in size. In short, we have a planet at last. So we've got our planet. But how do we know this is happening? How do we know there is a planet there? Because these are quite small. Even 1,000 kilometres is quite small compared to the star. And these planets, they don't give off much light. They're not fusing hydrogen at all. They're not burning. They're not doing anything. They might reflect a bit of the starlight, but it's very difficult to see them. And they're still surrounded by lots of dust and gas. So there's other things that we have to look for to try and see these processes. So I'm going to try and demonstrate it a bit with this video, if I can find the play button. So we're starting off with a molecular cloud about 1 solar mass in size, and it starts to contract, and you can start to see it spinning, and it's going to have a bit of instability, and it's going to start to go a bit weird. And it starts off quite nice and spirally, and it just goes into a bit of a mess, really. And by the time it finishes, nearly there. So you can see now you've got some density spots in there. So this is a map of density. So this isn't light, this is the density of the material in there. And you can see that there's quite likely going to be maybe a planet forming here, and you've got these wonderful spiral arms coming around it. This is material being dragged and distorted by the planet that's in the system. So we might not be able to see the planet, but we should be able to see these wonderful structures that exist. So we point our arrays of telescopes, and we see things like this. This is a real image of a real disk, and you can see these beautiful spiral arms, a dual spiral arm system, which looks kind of similar to what we just saw. So what is causing these spiral arms? Well, we like to think it's a planet. There are some other theories as to some instabilities and turbulence that can cause these sorts of things, but the preferred theory is things like this. We can attribute to some sort of disturbance by a planet or a large body, or there's something in there causing these spirals. And it's not just spirals that we see. We can see disks like this. So this is a disk called HL Tau. This is in the Taurus star-forming region that I showed right back at the beginning. And you can see these wonderful gaps and ring-like structures in the disk. And this is caused by a planet again. So we theorize if we put a planet here, as it goes around, it sweeps clear its orbit. Material near it is accreted in, material a bit far away is maybe pushed away by turbulence, and you end up with these lovely gaps in the system. Kind of looks a bit like Saturn, really, with all these gaps. And it's the same sort of process. So Saturn has moons, which there's one moon which is inside Saturn's rings, and there's several moons outside. These cause gaps through gravitational resonance, and it's a very similar system. Except this, of course, is much, much bigger. And you also see things a bit like this. This is some sort of weird crossover between half a spiral arm, half a gap here. And this was taken by my supervisor just last year, and they put a planet about here. And this long tail is a dust track behind the planet, which it drags around with it. And so we're fairly confident there's a planet there. We might never be able to observe it, but we can see the effects of the planet in the system. How long do I have left? Quite a while. Okay. So we can see there's a planet in here, even if we cannot necessarily directly observe it. But we can observe, I'll just skip past that a second, is what the next stage is. So this is a bit beyond what I study. I more focus on the spiral arms and the asymmetries in the disks, but later on in the life cycle of these things, all that gas that I talked about, the 99% gas, is gone. It's either been pushed away by stellar radiation, it's been accreted into the planets or onto the star, and so you're just left with the leftover dust that's in the system. We call these debris disks. It's the debris from a protoplanetary disk. And because all that extra stuff has gone, you can start to see the planets that are in there. So this is the very famous Fomalhaut system, and this is Fomalhaut B. It is there, I promise. It's that little few pixels of brightness that you can observe, and we can now observe directly planets. In this system on the left, there is supposed to be 4 planets, B, C, D, and E. I'll leave it up to you as to how well you say they're there, but the astronomers believe they're there. And so we can now observe these processes from start to finish. We can observe the planets being born inside their disks, we can observe the dust clouds that the stars first formed from, and we can observe the end result. We can see the planets, we can see the debris disks that are left over. But if I just go back to this again, so the protoplanetary disks that I observe, every single one is different. There's no real similarities between these. They're all different, and every single one we observe is different. We've only been able to observe these disks for like 5 or so years now with the current technology that we have, and the sheer variety is quite staggering. And that's why we love to observe these disks. There's just so many different weird and wonderful ways that these planets form. And if we want to truly understand how our own solar system formed, how our own planet came into being, we need to look at these disks and try and understand the different ways in which they form. So going on right here now is just a sample of all the various simulations that MatthewBeta has run, just showing the sheer variety of disks that you get. You get disks around 2 or 3 stars, you get multiple disks in close proximity interacting, you get fast disks, you get every disk you can imagine. You can be simulated, and a lot of them have been observed now. And so it's a really exciting time to get involved in observing these disks and finding all the different weird and wonderful things that are going on. And so if I leave that running, and I'll just say thank you for any questions. It's been a little bit quicker than I expected, but yeah, if you have any questions, thank you.